Check 1, 2, check, check.
Yeah, sorry about your class yesterday. There was like a universal problem.
I know.
It was a crappening all across campus. There were issues with all the Zoom rooms.
Yeah, I know. Everything else was set up. It was just the camera. So
Yeah,
I figured those.
we lost the camera feed to like 8 different rooms. So like it's fixed now. But yeah.
I was just worried that it would continue today because.
Yeah, no, they were working last night and this morning.
Yeah. What was the problem?
It was a resolution thing with their adapters that adapt the video signal going into like the Zoom Mac Mini, I guess. So there's an issue with the red camera resolution and update their adapters.
Cool. Thank you. Well, you're supposed to point to the stick and not the broom. Oh, I'll try both. Morning. Okay, the classroom is even more sparse today than Monday. Okay. Morning, everybody. Let's begin. Can you guys get your name tags out? So, Mohammed, what was the last topic we covered? Again, laptops shut and all that good stuff, guys. What was the last topic we covered? Autoencoders. And so, what did we learn about autoencoders, Emiliano? Yeah. Okay. So, Mara, maybe you can help me. What does the autoencoder learn? So what it does? Okay, Shantanu, what does the autoencoder do?
There's an initial encoding there that I think gets the features down, and then there's the decoder.
And what does the decoder do? Reconstruct the input. But what was it learning in this process? What was the autoencoder learning? Ron, maybe you can help me?
I'm thinking about it, yeah.
Okay, let me go back and make this simpler. If we only had linear activations, what was the autoencoder learning? If you had only linear activations, yes.
Transform that would transform into a space that would separate the data.
Separate the data? What was it doing? Come on, guys, we had like an 18-minute lecture on this. So, Anne, you can tell me. You've got your name upside down. Okay.
If it's linear, we are learning the
And what were their weights? Okay, let's drag this out of you guys. What was it learning? Someone want to help me?
I think it's linear projection.
The linear projection, it was learning a what did we say? We said it was learning a principal subspace, did we not? If you had a linear activation, then it was learning, basically it was learning the subspace on which most of the information in the data lies, and the error was everything that was not on the surface. Do you remember that? Clear, right? That was what we learned when we had linear activations. What happened when you learned when we had non-linear activations, Myra? We were learning a correlation. What were we learning, Alistair?
Curved manifold.
A curved manifold. You are learning a principal manifold. You remember that? Okay. This is a lesson because, I want you to remember this because that's what everything that we do with diffusion models and variational autoencoders and everything else builds off. And so, what was the very last thing we did in class?
Reconstruction of music instruments.
Reconstruction of music instruments. What were we taking advantage of when we did this? The decoder. How did we use the decoder?
Give it random input, and it would still map it to those possible space of musical instruments.
Because if you gave it any input, then basically it was only going to reconstruct things on the manifold, because that's all the decoder can reconstruct. Do you remember this? Right. And so that was the whole point of that particular exercise. We were showing you that when you train an autoencoder, the decoder learns the curved manifold that all data lie on from that class. And so anytime you pick something, you're actually going to pick something off that manifold. Do you remember this? Okay. So here's a new problem. I'm giving you a large collection of images of faces. Can a network learn to generate new portraits? Sample from this distribution of faces, right? Based on what you've learned in the last class, how could you do this? Yes, Alistair.
Autoencoder over images, make it reconstruct the same face. Then afterwards, the inference detach just the decoder and feed it arbitrary space.
Fantastic, right? That's the lesson I was hoping you'd take, right? If you trained an autoencoder on just images of faces, the decoder is going to learn the manifold that faces lie on. If you pick a point on it, it's probably hopefully going to be a face. Same thing. If I asked you to give you a large collection of landscapes and asked you to train a network to generate new landscape images, you do the same thing. You'd probably train an autoencoder, and the autoencoder is going to learn the structure, right? Now, the hypothesis over here is this. Images of faces, they're all faces. There's a very distinct structure to it. Images of landscapes, there's a very distinct structure to it. So now, suppose I gave you, now everything in this world lives in some high dimensional space. Photographs, what is the dimensionality of the space they live in? If I give you a 1,000,000 pixel image, what is the dimensionality of the space it lives in? Come on, guys. It's 1,000,000 pixels, it's 1,000,000 dimensions, right? It's 1,000 cross 1,000, it's 1,000,000 pixels. Every photo picture in 1,000,000 pixel picture is a point in a 1,000,000 dimensional space, yes or no? Can everybody say yes? Yes. Okay, so guys, Wake up. This is what I want you to remember. So now, hypothetically, imagine this is my million dimensional space. If I had this scatter for your data, do you think the scatter could represent the scatter of faces? Yes or no? Fills up the space. It cannot. There is no structure to it, right? There is no pattern. Anytime I say every image is that of a face, it means it has some structure to it. The moment you add some structure, what are you taking away from the data? You're taking away degrees of freedom, right? It has to be somewhat facial. Boom. It means that it can't fill the entire space. It has to be something maybe more restricted. Maybe all of this is gone, right? These are not possible. Then I say it's supposed to have ears. It has to have noses. So every single restriction that you put on it is taking away degrees of freedom from the data. Yes or no? Right. The only thing that fills up the space is going to be random noise, right? You don't want to be random noise. And so anytime you look at data from a particular class, then that data is going to lie. If you look at all the instances of that data, they're structured, they're going to lie on some low dimensional manifold in a high dimensional space, right? Because degrees of freedom are taken away. And so that is the hypothesis that you're going to work on. The data are distributed according to a curved or otherwise nonlinear manifold in a high dimensional space, and the principal components of all target instances of this target class lie on the space. Of course, there will be some variation. So maybe you're going to have some fuzz off this manifold. And so when I'm asking you to generate new data from this class, what we really want to do is to figure out what this curved manifold is. Does that make sense to all of you guys? But is it enough to just characterize this curved manifold and know it, or do you need more? What would you think? What do you think? You need more? What more would you need? So here's the thing. If I have this curved manifold, not every point on this is going to be a face, right? There's some regions where you probably have faces and others not so much, correct? And so you even need to know where to sample from it and where the faces, most faces really lie, the distribution of faces on the surface. So if I want to generate new faces, I need to learn to characterize the manifold, and I need to know how to pick points on this manifold. Is that making sense to everybody, right? And we saw one instance of how you can learn this manifold, the autoencoder. The decoder, we saw did nonlinear principal component analysis, and we saw that more complex, deeper decoders learn more complex surfaces, and then you could pick some points on the surface, and if you picked arbitrary points just right, what you would get is instances of the class that you were trying to, that you learned it from. And in this case, we saw that, we got examples of saxophones by picking points, but then I didn't tell you something. I was very careful. I cheated. How do you think I cheated? Yes. I see a smile on your face, so you know the answer. Okay, there was a smile without an answer. How would I have cheated? Not every point on that manifold is going to sound like a clarinet note, right? I must have tried this thousands of times till I got an example where it sounded like a clarinet note. Make sense, right? That's how I cheated, because I have to give you presentable examples in class. And so, but then, using the same approach, if I want to train a network to learn the pictures of faces, I could train an autoencoder, and then the decoder learns the face manifold. Every instance on it hopefully is going to be the face, but not really. For some specific inputs, some locations on this manifold are going to represent valid faces. And then, so we can use the decoder by inputting some arbitrary z, and so long as the z is okay, it finds the right location on the manifold, you're going to get faces. So, but there was a problem. We don't know what these z values are because there were no constraints when we were training this network. I showed you this example with the spiral, right? Data just off a spiral. And the encoder actually, the decoder actually learned the structure of the spiral. And so what we did over here is we've trained the autoencoder, we got the decoder, and then we let Z go from minus infinity or very large negative value to a large positive value. And as you keep plotting it, as Z increases, you find that as you're reconstructing the curve, the spiral, but not exactly, right? What is happening over here is this. Not a very good point. Okay. You see, observe that it's going around, but then over there, it didn't continue. It jumped over to that side and then went around this way, then jumped back in and went back out, right? Why is that happening? Because on your training data, you have no control over how Z's, on Z's. So you might find that for the first portion of the spiral, the Z's are contiguous. Then for the rest of it, it didn't continue over there, it went to some other location. And so when I just vary the Z's, it is reconstructing the spiral, but a lot of other gunk that represents portions of the Z that were not the training data. And it's not maintaining continuity. We saw this also with the sinusoid. Okay, here's your first ball. Okay, we'll call out some Pokemons. Anybody want to be called out? Okay. So we're missing Jeffrey and his skills. Celio. Who's Celio? Celio present? No, Celio is absent. Okay. Who's wheezing? Wheezing's absent as well. I have a feeling that this is not going to work today. None of them are in class. Monferno. Who's Monferno?
Oh, that's me.
Okay. First statement, true or false?
I think it's false.
It's false. Is that correct? Is the first statement false, guys? It's true, right? Okay. We got one of our Pokemons. Who's Wingull? Wingull's absent. Ponyta. Who's Ponyta? Ponytails. Okay. Can somebody tell me about the answers to the second question?
The second one?
Which statements are true and which are false? Only the middle one. Okay, right. So the decoder can only generate data on a low-dimensional surface on the space, and the true dimensionality of this manifold cannot be greater than the dimensionality of the latent representation that's presented to the decoder, right? Yes.
Why is the first statement true when you have sparse autoencoders where your bottleneck can actually be much bigger than the input?
So the point is that is a cap, right? So whatever the width of the bottleneck, that is the upper bound on the manifold. So if you have, the data can be on some sub-manifold within that manifold, that's the upper bound. Okay, I mean, I can imagine a curved sheet and a line on that sheet. I could be down on that line, but it's still going to be on the sheet. So the problem is we do not know what the Z's are. We have no control on the Z's. So what's the first thing we can do? If I just train my network like so, we didn't have any control on the Z's. So when I picked a point on it, there was no guarantee that it's actually going to give me a point on, a valid point. If I fed in a random Z, I could end up getting data on the bar or on the curve outside, and those would not be valid points, right? So how can I modify this process to make sure that I'm actually have some idea on what Z's to feed in? Yes?
You want to choose these that represent your class.
I want to choose Z's that represent the class, but if I just train the autoencoder any which way, do I know what those Z's are? Okay, so then what can I do?
Start from a particular, always start from a particular set of points.
Always start from a particular set of points. Can I do? How about imposing a constraint on the Z's when I'm training the autoencoder so that I know where the Z's lie? Right. So here's what I can do. I can say that I want my z's. I want to say these can't be anything. Z's have to be some distribution around 0. That's a perfectly valid requirement to have, right? And so I can do that, and then, or I can say the z's must come from a Gaussian distribution. But then the problem is, how do I train an autoencoder to ensure that the hidden representation z has a specific distribution like a Gaussian? By the way, why is this thing over here? Can somebody hear it? Oh, very bizarre. Maybe I can grab this and move it. Nope. Okay. All right. So again, keeping in mind that the decoder and the encoder can be very complex, and let's assume that each of them has its own set of parameters, right? So how would I impose a restriction on Z during training? Any ideas?
Add a loss to it.
Add what kind of loss?
Like divergence from
Divergence from a standard Gaussian. Beautiful, right? So here's what I can do. First, what is a standard Gaussian? A standard Gaussian is this perfectly symmetric bell-shaped curve, right? It's isotropic. If you take a slice at any height, it's always going to be a perfect circle. Furthermore, the different variables are going to be independent. So if you look at the joint distribution of any z1 and z2, it's going to be the probable product of the probabilities of the individual z's. And finally, if that's the standard formula for the standard Gaussian. It's just going to be 1 over square root of 2 pi raised to d e raised to minus 0.5 norm z squared, because it's the mean is 0. If you take the log of that, that's just going to be 0.5 d log 2 pi from the first guy, minus 0.5 d log 2 pi minus 0.5 norm z squared. The negative log is 0.5 norm z squared plus 2 pi raised, log of 2 pi times some constant. Anyway, this has this other property. If I can just impose this, if I want to impose a constraint on z, I want to minimize the error between x and x hat as before, but then I want to also impose this requirement that the probability distribution of z must be as close to standard Gaussian as possible. There are a couple of different ways to do it. One simple way to do it is to say, I'm going to compute the probability of the z's that I get using a standard Gaussian. And if my data does indeed come from a standard Gaussian, the maximum likelihood principle is going to say that this log likelihood is going to be high, right? So let me try imposing that as a loss. So this guy, which is to say, I'm going to minimize the negative log likelihood of z as computed from a standard Gaussian, while also training my autoencoder. And the negative log likelihood of z, as we just saw, going back here, is this guy, right? There's some constant. You can't minimize it. All that remains is 0.5 norm z squared. And so and the 0.5 is again a scalar. It doesn't matter. So I want to just minimize norm z squared, which is norm of the encoder operating on x whole squared, right? And so I can add that to my loss. I'm going to add that to my reconstruction. And then I add the second term, which is lambda times the encoder times encoder applied on x whole squared. Would this work? Would this work? Anybody? I have some examples, which unfortunately I didn't put into my slide, but here's a poll for you guys. Okay, someone want to answer the first question for me? Someone on Zoom. First statement, true or false? Zoom?
It's
Is there
true.
anybody?
It's true.
Okay. And the second one, true or false?
False.
False.
Let's check, yes. A regular autoencoder trained to also minimize the length of the hidden latent representation implicitly assumes that the z's have been drawn from an isotropic Gaussian, right? And so the output of an AE trained in this manner is still going to lie on a low dimensional manifold. All that happens is that the location on this manifold that the data are coming from is being kind of restricted, right? So this is what we do. But then here's a problem. This won't really work. I have some nice examples that Naisha computed, which I didn't manage to quite get on the slides. What would happen if I minimize norm z squared? I'm just minimizing this. What would happen to this? Is the distribution of z going to be Gaussian? Is it going to be a Gaussian with unit variance? What do you guys think? I'm just minimizing norm z squared. Come on. What would happen?
It would be quadratic.
Can you say that loud?
It would be quadratic.
It's quadratic, but the point is all that is going to happen is that if this is z and this is p of z, it's going to push everything towards z equals 0, correct? And so the distribution for z's that you get is going to get something like this, something really close to 0, whereas your standard Gaussian looks like this. Make sense? Because you're just making z 0. You have no additional constraints. You have no constraint on the variance of z. You're just saying make z small. And as a result, even if not only are you unlikely to learn this manifold right, the point, you're only going to learn the location of a single point or some regions very close to a single point where things look like faces. If you draw z's from a standard Gaussian, which might be z's from here, the output can be any odd rubbish. Okay? That makes sense? Right. And so inputting Gaussian data into it is still going to produce what the decoder is able to produce, which means that it might have got the manifold wrong away from z 0, and the range of z's that it can accept is still very small. So you still don't have any control on this whole process. So back to the drawing board, right? The decoder can only generate data on a low dimensional manifold of the same dimension as the input to the decoder, right? Now, here's a different way to think about it. We saw this in the last class. What does the network do? It starts with this flat surface that we've got, which is the input, and keeps twisting and turning and warping it and putting it in higher dimensional spaces. And the dimensionality of the space doesn't ever increase. It's not going to be larger than the input. It can decrease from the input, right? It's going to be bending and folding it and pushing it into higher or lower dimensional spaces. At some points, it can actually project it down, but it's just going to be bending and folding it all the time, right? And so you're trying to start off with a standard Gaussian on some n-dimensional space, and you're trying to warp and fold this using the decoder so that it actually ends up looking like the curved manifold that you have and some distribution on the curved manifold. Make sense to all of you guys? And this is what we're really trying to do. And the objective over here is this. If I have some data of this kind, so let's, where did I keep my chalk? So let's say I have some data of this kind. Of this kind, okay? And if I use only one hidden dimension, then what is the dimensionality of the manifold? If my latent variable is 1, what is the dimensionality of the manifold? Come on, guys. 1. Can everybody say 1 loud?
1.
Okay, it has to be the dimension or less. It can't go below 1, right? So it's going to learn a curve. Now, suppose I have only one hidden layer. Can it learn something that keeps folding back and forth? It's going to learn maybe just a line, right? So the number of layers is going to give you more and more modes in your input. So maybe it learns something like this. Maybe it even learns a quadratic. What are you really doing? You're trying to fit a quadratic curve to the scatter of points. Correct? Can you do it perfectly? No, there will be an error, right? And so here is the issue, right? The actual dimensionality of the manifold is unknown. You're just guessing it. And so if you guess it, odds are you're going to end up in a situation of this kind. And so you're going to have a lot of error. You're not accounting, the simple autoencoder is not accounting for this error. You might actually end up learning this manifold. Will picking things from this manifold give you faces, for example? Will it? No, it will not, right? You need to have a sufficiently high dimensionality, right? Second, let's assume I got the right dimensionality. Then it's probably going to learn an error of this kind. Let's say it does that. In this case, is every point on the every face a point on this manifold? It's just capturing the principal manifold, right? But there's always some error off of this. Can you reconstruct your training data perfectly? No, right? And so our simple problem over here neither captures this phenomenon. This is going to give you rubbish all the time. And even here, it's not accounting for the fact that you're actually going to have some error of the manifold. That makes sense to everybody? Right. And so how can I account for this? Let's assume that I actually got a dimensionality which is high enough to capture this guy for my z's, okay? If I do this, will it actually learn this curve, or can it, you're just training this, right? Or can it learn something of that kind? Is it actually going to learn the curve? Yes or no? Any guarantees? No, okay. But if it learns the curve, what can we say about the error? It will be low. Here's something else you can say. If you've given it enough degrees of freedom, eventually the error that remains is everything that cannot be captured by this manifold. If there's any structured nature to the error, then the manifold would have already captured this. So the error is going to be unstructured compared to the data itself, right? What is the most unstructured noise you can think of? What kind of random? White what? Gaussian. The most for any given weight, the distribution that has the highest entropy is the Gaussian distribution. If you learn your manifold right, then the error must be Gaussian. Because if there was any more information from it, the manifold would have captured it. That makes sense? Right. And so that's what we're going to do. We're going to try to minimize the error between the output of the decoder and the actual inputs. And we're going to try to say, if we learn this right, that error is going to be Gaussian. So that gives us this model. Your Z goes into the decoder. It comes up with a point on the manifold. Then you're adding some Gaussian noise to it to actually generate the data that you got. Everybody good with this, right? And so here's the problem. Once I figure that there is noise, X no longer is a deterministic function of Z, is it? For any given Z, I'm going to transform it to a point on the manifold. But then I'm adding noise, and noise cannot be controlled, correct? So the same point on the manifold can result in different outputs. So conversely, if you give me an actual data point, is there a unique point on the manifold that could have generated it? Is there? Because the noise is random, right? If I give you a point here, it could have come from here, or here, or here, or here by appropriate addition of noise. So this is, so here's what, the decoder is now a generative model. What happens? This business of accounting for the noise has converted our model. It's made it something magical. It's learning a distribution because of the addition of the noise. The decoder by itself has the only randomness in the decoder is the randomness of the Z that comes into it. But even if I fix Z, the output has a distribution, which is the distribution of the noise. So the overall process has now become a generative model. This just less, right? And so this one, the decoder is a generative model. It has a generative story. You say that I'm picking a random Gaussian from Z, from my standard, random input from my standard Gaussian. I'm processing it through the decoder, which is placing it in some point on the manifold, and then I'm adding some noise to it. A different way of looking at it is that The decoder, my standard Gaussian has some distribution in, say, two-dimensional space in my example. The decoder is going to convert this to a surface. What is the dimensionality of the surface? If the input is two-dimensional, what is the dimensionality of the curved surface in the higher dimensional space? 2, can't be more than 2, correct? And so the decoder is going to warp and bend this guy. And let's say I'm in 3 dimensions, it could be in 1,000 dimensions, you're going to have some surface, right, on the space. And this Gaussian is going to get twisted and turned, and it's going to become something out here. And so the generative process says that the first step is to draw a sample from this Gaussian on this manifold, and then the second step is to add some noise to it. And that's the generative story behind your data. And so I want to train it. The way I will do it is if I'm given Z, the Z for every input, then I'm going to pass Z through the decoder, and I'm going to try to minimize the error between the output of the decoder and the actual training data instance. And why do I just directly minimize the error between the output of the decoder and the training data instance? Because by assumption, if you do everything just right, the noise must be zero mean. Because if the noise were not zero mean, then the decoder would have captured it, right? And the noise must have no structure. It must be uninformed. Otherwise, the decoder will capture it. So this is the best you can do. If you minimize the noise, you're going to learn the decoder that fits the data, the decoder that fits the data just right. And so all we need to do, if I have Z, is to minimize this. Everybody good with this so far, right? So this means that if I want to train my model, I can focus on the decoder. And if I focus on the decoder, I can just say that every training data instance, let's say I have faces. So I've got somebody's face, okay. Whose face am I drawing? Yours, okay. She has hair, right? And glasses. Okay. And unshaven. Okay, I've got this face. And this is the output of my decoder, right? And so now I've got this Z. Sorry, it doesn't look like you. You're much more handsome than that. But then this is what I'm supposed to be getting. I get some output over here. I'm going to be just minimizing the error between this guy and this, right? And if I do this, I should be able to learn the D. Can I do this? Just given a picture of Ritwik's, several pictures of Ritwik's face. Can I do this? Or is something missing? What's missing? Ibrahim, what's missing? Do I have the Z that went into the decoder? If I don't have the Z, what is the Z that the decoder is operating on? We don't have that, correct? And so I can't, although this is the generative model, I'm missing critical information. The critical information is what went in to generate Ritwik's face. If I had the Z, I could train the decoder to just minimize this error and everything would work. That makes sense? Make sense to you guys? Right. I don't have Z. Solve this problem for me. Ibrahim, solve the problem for me. Yeah.
Give some noise.
Give some noise, but noise is not the correct Z, right? So, well, that's kind of getting there. You had an answer?
Can you explain why we don't have Z?
I gave you a picture of Ritwik's face. Where's the Z?
Pass that to the encoder, right?
So this is, I'm only giving you the decoder, right? We're building this up. We don't have the Z, right? But that's your answer. So because I don't have the Z, I'm going to guess the Z. For every input over here, I'm going to guess the Z. And then if I guess the Z, I have a combination of Z and X. I can pass the Z through the decoder. I get an output. And then I can minimize the error. That make sense? How do I guess the Z? I'm going to stick in a, we don't have the Z for each X. So that's what the encoder is doing. For each X, I'm going to guess the Z Then I'm going to put that z through the decoder, and then I'm going to minimize the error. Make sense to everybody? Right here.
When you're minimizing the error, are you changing the z that you're
No, you're fixing the z over this, right?
fixing the z?
Yeah, because this is, you have input-output pairs. The input is z, the output is x, correct? Except I'm guessing the z, and the z is coming from an encoder. Except now, is it possible for me to actually find a unique z for any phase? The thing is, there are many points on the output manifold that can all give me the same phase. There's no way for me to say this phase came from this z. There's an entire distribution of z's that could have generated the phase, correct? And so this means there's a distribution of z's, all of which could have generated the phase. So now is the encoder, which guesses a single z, sufficient? What must the encoder do? Yes.
Find the distribution.
It must find the entire distribution of z's, correct? The encoder must actually give us the entire distribution of z's. This gives us the variational autoencoder. The encoder finds the distribution of z's that could have generated the phase. And then every point on this distribution is going to be passed through the decoder, and you're going to be minimizing the overall error. That makes sense to everybody? How we actually built up to this. Make sense to you? Okay. But then so the problem is, so the encoder computes the distribution P of z given x. What are the z's that could have generated this phase? And then the decoder converts all the z's in this distribution to the phase, and you're minimizing the error, okay? Or it might typically take one sample from this distribution and try to convert it to a phase. So if I want to train the encoder, if I have this whole process, then for every input I'm going to have a z, and now I have the x because the z has been given by the encoder. So to train the decoder, I just take the x's and the z's, and then I can train the decoder, right? And that's going to give me the phi, but then the encoder has to guess the z's. And where do the encoder parameters come from? Now this becomes a coupled phenomenon. The encoder has to be trained to generate the distribution of z's that, when passed through the decoder, is most likely to construct the phase. Make sense? How about the encoder and the decoder are now coupled and linked to one another, right? And so to train the encoder, you want to estimate the theta such that the z's can be decoded into the phases. And to train the decoder, you want to estimate the phi such that those z's are converted to phases. This is good to everybody? Okay. But then there's something more, right? What did we say about z's? Does this localize z's? The distribution can be anywhere, right? You still want to localize z's. And what was the location constraint we wanted on z's? Zeros. You wanted it to be from a standard Gaussian, right? And so we want to say that the z's, overall distribution of z's, must come from a standard Gaussian. And the conditional distribution of z's for any particular input only comes from a small region of this distribution. Make sense to everybody? Right. And so what does this mean? I know that the conditional distribution of z for any given input can only be a small section of the standard Gaussian. The overall distribution of z across all inputs must be a standard Gaussian, right? The whole thing has to be coupled. So what this means is that if I looked at all of my training data and looked at the conditional distribution of z for all of the training data and integrate this over all of my training data, that result must look like a standard Gaussian. Make sense? Right? So you want to make sure that p of x, the integral of p of x, p of z given x dx, is a standard Gaussian. Zoom, any questions? Was this too complex already? Because this is the easy bet.
So I have a question.
Yeah.
So going back to the manifold question, so how do we get a manifold that is true to the true manifold. We talked about adding Gaussian noise, but that was to minimize the error on the manifold, right?
Exactly. So here's what happens. Now, if I learn this manifold, is the Gaussian going to be small? Is the error going to be a small Gaussian with a small variance? The one on the board.
Sorry, which one? It should be large, right?
If I have this, the errors are going to be large, right?
Yes.
So when will the errors be smallest? When the manifold actually passes strictly through the data, right?
Mm-hmm.
And captures all the structure to it in it. So by minimizing the reconstruction error, you are learning the manifold. That answer your question?
Okay. Yes.
Okay. Here's another thing. P of z given x, what kind of a distribution is it? We really have no idea, right? Because the decoder is a very nonlinear, complicated thing. And it's taking the standard Gaussian and it's bending it and warping it, right? And so if I look at all of these guys out here, we said there were many points on this manifold that could have become the space. So if I look at the distribution of all of these guys in the input, this could be some crazy distribution of this kind. And we don't know how to characterize it, right? That makes sense? Because you're folding this back. And we don't know what that shape is going to look like. So then what do I do? Anybody? Any guesses? What can I do? Someone on Zoom, can you take a guess? I'm running out of time. Okay, if you can't take a guess, I'm going to rush through the rest of this lecture. I'm giving you one last chance to guess. Counting down 5, 4, 3, 2, 1. Okay, done, right? I'm just going to assume it. I'm going to guess, right? So what I can do is to say, I have no idea that this distribution out here could be some funky thing like this. I don't know how to build this, but I do know how to build Gaussians, correct? So I'm going to try to assume that it came from a Gaussian. But I'm going to learn it such that this Gaussian is so compact that it's as close as possible to this guy. That makes sense to everybody? And so instead of deriving the true P of z given x, we derive an estimate Q of z given x, which is actually a Gaussian because Gaussians are things we know how to deal with. And then we also ensure that the z given q, this approximation is as close to the P of z given x as possible. Make sense? Right. And so the encoder actually computes an estimate Q of z given x of the actual prior posterior. And I want to make the encoder is now trained to estimate Q, but the Q should be as close as possible to the unknown P as we can get it. So you want to minimize the KL divergence between Q of z given x and P of z given x. Everybody with me? Zoom?
Yes.
This makes sense? Okay.
Yeah.
And that's going to be, and now we have a bunch of math, okay? Now, of course, we all love math here in CMU. So the KL divergence between Q and P is simply the expectation over Z's of log of Q over P of Z given X, right? And I can rewrite this P of, which is expectation over Z's drawn from Q of the log of Q of Z given X minus the expectation over Z as log of P of Z given X. This can be written as using Bayes' rule as P of Z times P of X given Z divided by P of X. So expanding that out, that's simply going to be, again, the expectation of log of Q. This is over Z's drawn from Q, minus the expectation of log of P of Z, minus the expectation of the log of P of X given Z, plus the expectation of log of P of X. P of X is the true distribution of X. It's not a function of any network parameters. So this really is not something that you would bother to minimize. The interesting thing is that if you look at the first two terms here, the first two terms here simply the KL divergence between the Q of Z given X and P of Z itself, the standard Gaussian. So, and the second term is simply the negative log likelihood of the distribution of X given Z. Okay, this making sense to everybody? So you basically end up trying to minimize the KL divergence between the conditional approximated conditional distribution of Z and the standard Gaussian. And the second one, can you turn your phone off, please? Don't do that. You know the rules. Yeah, it's very disrespectful to come and do this in my face. Okay? And the second term is the negative log likelihood of Z of P of X given Z. And what is that second term? That's basically the loss of the that we associate with the encoder. Everybody good with this so far, right? So this guy, this one here, this is for one term, but you're really doing this over all of your training data. If you're doing this over all of the training data, what are you really doing? You're taking the expectation of the training data of the KL divergence between the conditional distribution of Z given X as you approximate it and the standard Gaussian. That's basically saying that the union of all of those ellipses must look as close as possible to a standard Gaussian as you can get it. Make sense? Right. So that's what this first term over here does. So now that leaves us with the second term. Let's look at the second term. In fact, okay, so this expectation over X is basically you're taking the average over all the training data of the KL divergence between Q of Z given X and the standard Gaussian. And that's how we're going to be training the encoder parameters. So again, the encoder is not computing a Z for any X. It's actually computing an entire distribution for Z, okay? Now recall here that the Q of Z given X must approximate P of Z given X as closely as possible, which is this thing here. You want this to be as tight as possible. And so the which is the distribution of Z that could generate X, but Q of Z given X is going to have be able to generate some Z values which don't actually generate a phase. We're trying to minimize the volume of Q of Z given X that gives you non-phase images. That makes sense, right? And so that's what we're doing. And now the decoder is going to be converting these Z's from Q of Z given X to generate X. How do I minimize the volume of Z? Okay, for the encoder side, we know that what we want to do is to minimize the average KL divergence between the Q's and the standard Gaussian. That's because that's basically doing the picture on top. You're saying that the union of all of the ellipses must be a standard Gaussian. But then I also want to make sure that this guy itself is as tight as possible to this one. How can I do that? Any ideas? How would I do this? Someone, give me an answer. Okay, tell me this. If I randomly sample from this Q, and if that random sample fell from here, is it going to generate a phase? Yes or no?
Yes.
If it fell from here, is it going to generate a phase?
No.
No guarantee. We don't know. Correct? So how about I keep sampling from this Q, and I try to minimize the error? Because if I keep sampling from the Q and minimize the error, the region of the Q that generates things that don't look like faces is going to be minimized. Make sense to everybody? Every step of this is, there's a hell of a lot of math that they write when they put this out. But if you think your way through it, it's actually very, very straightforward. It's all very intuitive. You could have done this without the math. Okay? So again, the problem for the encoder lies in the decoder, because the decoder can convert things from this Q to a face. So really, we want to make sure that the decoder should be able to convert these guys and not convert these guys, which means for us to be able to make this guess, we need to know what the decoder is doing. So the problem in guessing the tightest Q is that we also need to know what the decoder is doing. The problem for the encoder lies in the decoder. And so we know that, and the reason it is a problem is that, remember, there's an error term on the output of the decoder, right? If I passed some sample from here through the decoder, is it going to generate a phase? We don't know. But then I can explain it off saying, it's really just noise. The reason, this thing can be completely accounted for by noise. Does that make sense? So when you minimize the error, we have to make sure that, because the surface is, very curved, we can explain all kinds of rubbish off as saying this came from the noise. And you don't want to be doing this. So how would I do this? How do I deal with this? First, we observe that if I give you any z, then the probability distribution of x is Gaussian. Why? Because for any particular z, there's only one x hat that comes out. The only randomness that remains, p of x given x hat, is the distribution of the error E itself, which is Gaussian. The lady over there, do you mind leaving the room? Please leave the room. I'm serious, leave the room. Because I've just told you right now that this is not okay. Okay, you can stay. Put your phone in the bag. Yes. Okay, we need to make some simplifying assumptions, right? To make all of this work. And that's because P of z given x is not characterizable, again. And so we want to minimize this error between this guy and this guy again. And we don't know this. So here's what I'm going to do. First, I don't know what Q of z given x is. I have not specified Q of z given x. But I said I'm going to assume that it's Gaussian because I need to be able to characterize Q. I have a justification for it. Here's your standard Gaussian again. It's isotropic. If I slice it at any point, that slice is still going, the outline is still going to look like, what's it going to look like? It's still going to look like a Gaussian, correct? And so it doesn't matter where I slice it from, it's always going to look like a Gaussian. So long as the slice is linear, the slice is a Gaussian. Now, but for any given x, is the set of possible z's that could have generated that x linear? Not really, right? So I'm going to make an assumption that the set of possible z's that resulted in this region on the manifold that could have generated the x comes from a very gentle curve. If it comes from a very gentle curve, then the distribution along that curve is also going to be approximately Gaussian so long as the curve is not too far away from being linear. Make sense? Right? And then it's going to have a mean, and it's going to have, basically, so long as the encoder output, the error between the curve and the line is very small, within the region of the Gaussian. It doesn't matter how bad the error is, very far away from z equals 0. If that error is small, I can approximate it as Gaussian. That Gaussian is going to have its own mean, it's going to have its own variance, and the mean and the variance are actually going to be functions of the input x itself. Make sense? And so P of z, given that the encoder output is the phase, can be approximated as a Gaussian, and the mean of this Gaussian and the variance of this Gaussian are going to both depend on x. Right? Make sense? Yeah. I'm going to try some Pokemons on this one. These are two simple answers. And so we have a few minutes. Who's Sankern, S-U-N-K-E-R-N? Do we have that person in class? No, Sankern's not in class. Who's Girafarij, G-I-R-A-F-A-R-I-J? In class? Nope. Okay. Who's Altaria, A-L-T-A, no, A-L-T-A-R-I-A, in class? Okay, I give up. Can somebody answer the first question, true or false? And folks on Zoom, second question. True or false?
True. Also true.
Yes. The z is a random vector with an isotropic Gaussian distribution. So the conditional distribution of the projection of z on any affine plane is also going to be Gaussian. if Z is a random vector with an isotropic distribution, the conditional distribution on a curved surface that is not too curved within the region of the Gaussian is going to approximately also be Gaussian. This is what we are depending on. And that's why we hope to be able to get a Q which is tight enough with respect to P, right? And the assumption over here is that this P is not going to look like this. The assumption is that this P is kind of looks Gaussian, which is why I can put a tight Z on it, okay? And so here's what we have. I'm going to make the average Z, Q of Z, as average Q of Z given X as close to the standard Gaussian as possible. This is the model. The encoder, we saw, computes the distribution of distribution Q, and that Q we are going to assume is a Gaussian. And so what the encoder is going to learn, estimate, are the mean and the variance of Q. Together they give you a Gaussian, right? And so I'm going to be approximating P of Z given X as this Gaussian whose mean and variance have come out from the encoder. And for convenience, I'm going to assume that the variance is a diagonal matrix because you can assume any odd thing when you begin making approximations. And so that Q is going to be a proxy of P. So that gave us what's happening out here. And now if I want to estimate theta to make the Z's that can be encoded more probable, basically, if my Q is very tight, then most of the Z's are going to come in the region of P that actually generated the data, correct? And so they will have high probability. So I can explicitly say the Q sampled from Z, the Z sampled from Q, when they generate faces, these must have very high probability. That makes sense to all of you guys, right? And so what is the probability of X given Z? We know that that's just the probability distribution of E itself with the mean shifted to P of Z, decoder of Z, right? And so I'll make another simplifying assumption that the error is standard Gaussian, is a isotropic Gaussian. This need not be true. Okay, if the error has a covariance that's non-diagonal, that represents structure, right? And so if it represents structure, then you expect the decoder to learn it. The most uninformed Gaussian is one with a diagonal covariance. So it's reasonable to assume that the error covariance is diagonal. It's not so reasonable to assume that it's going to have the same variance along every component, but we will assume it because we want to make our math simple, okay? You can do this without the second assumption. And so the probability of the data X given any Z is just given by the log Gaussian, where the mean is the decoder at Z, right? This makes sense. And so this guy, over all XZ pairs, you want to train the decoder such that this negative log likelihood is minimized, which is to say the probability of the X given Z is maximized, which is basically saying that so long as the Z's came from this Q, if the probability is maximized, you're probably coming from the region of Q that most overlaps with the P, right? And so you can just learn this using backpropagation. So this is argmax, and so argmin is just this guy. I can define this loss for training my decoder. And we are saying that the Z's themselves came from Q, right? So, but then the Z's come from Q, and Q is a function of phi, right? Because Q is an approximation derived from the encoder. Q is a function of theta. Theta are the parameters of the encoder, right? And so the overall loss, as you keep writing it, is that you want to train the log likelihood. You want to minimize the negative log likelihood of the training data. And you want to train the encoder such that when you actually compute the probability of the output of the encoder, of the decoder, that is maximized. Because if that is maximized, it means that the Q is sort of as tight as possible with respect to the P. Does that make sense to everybody? So it's very strange. You're linking the encoder to the decoder by saying that if the decoder is doing a perfect job, then the probabilities of all of the outputs generated from Z sample from Q should be very high. That's when the Q is catching the P of Z as tightly as possible. And so you're going to maximize the log likelihood of the output with respect to theta. So now, for each training instance, you want to do this over all the Z's that could have been generated from Q, but that's going to be a pain. So typically what you do is just randomly sample a Z from Q. And there are even odds that that Z is going to fall within the P region or in the region that doesn't overlap. So, that's how it works out, right? And so for each training point, Z is obtained as a sample from Q, which is that Gaussian that we just saw. But sampling is a non-differentiable process. So there's a standard reparameterization trick. How do you sample from an arbitrary Gaussian? You sample from a standard Gaussian. Then you scale it up by the variance of the Gaussian that you're interested in. And then you scale it up by the standard deviation of the Gaussian you're interested in. Then you add the mean of that Gaussian. And so this Z is actually a sample from a standard Gaussian times the standard deviation, which is the square root of the variance, plus the mean. And when you do this, there's no sampling process with respect to the mean and the variance itself. Epsilon is just a term that came from a standard Gaussian, okay? So this is the reparameterization trick. And now you can differentiate Z with respect to theta. So this is a sampled Z from Q. And this can be differentiated with respect to theta. And what about the decoder side? So if I want to go past the whole thing through, if I want to minimize the loss, which is the negative log likelihood of the decoder with respect to theta, I have to use the chain rule. I have to compute the derivative of the loss with respect to Z times the derivative of Z with respect to theta, and the derivative of Z with respect to theta can be obtained from this formula over here, okay? Again, I don't expect you to understand all of the math from my slides. I expect you to go back and look at the slides, but I'm just conveying the overall high-level idea, right? So any questions so far about how we got to this point? Guys on Zoom? Yes or no? Okay, no questions. It's too confusing. All right. Now the second is, how do you train the decoder? You want to estimate the phi such that for every sampled Z, the error is minimized, right? Which is to say the negative log likelihood of the generated data, of the training data is maximized. If you minimize the error, it's like making the variance of the error very small. Making the variance of the error very small is maximizing the likelihood of the data itself, right? So that's again just going to give you the log likelihood, which is the same formula that we had as before. Because even for the encoder, we were computing the negative log likelihood of the output of the decoder. And that's what we were differentiating with respect to the encoder parameters. And as far as the decoder is concerned, it's the same term. We're also going to be minimizing that with respect to the decoder parameters. So both of them end up just being parameters of being trained to minimize the negative log likelihood of the output of the decoder when it has been excited using samples drawn from the output of the encoder. Make sense? So overall thing, we are going to compute the negative log likelihood of the output of the decoder. We are going to train the encoder parameters such that that thing is minimized, which means the Q is fitting the P as tightly as possible. We are also going to train the decoder so that it's minimized, such that for Z sample from this Q, the decoder is doing as good a job of generating the output as possible. And then you're going to add a third term, which is to say that the Z's themselves must overall come from a standard Gaussian. Make sense? There are three different things going on over here. Yes, Alistair, you had a question?
These steps, do they occur separately?
They're all occurring together, right? And so, of course, we have the constraint on Z. You want to make the average Q of Z as close to a standard Gaussian as possible. And so I have one, and what is the KL divergence between the Gaussian Q and a standard Gaussian? We have a nice closed form formula for it. It's on the slide. So this term was simply the average KL divergence between Q of Z given X and a standard Gaussian, right? So for that, we have a formula. And so if you look at the overall loss, the overall loss is this guy. This is the negative log likelihood of the output of the decoder computed on samples drawn from Q. And this is the average KL divergence between the Qs and the standard Gaussian. So the loss has only two terms. Does that answer your question, Alistair? Right? You're doing this simultaneously. And all you would be doing is differentiating this with respect to all the network parameters to get your get both the encoder and the decoder simultaneously. That makes sense to everybody? Guys on Zoom, did the whole process make sense? The math, I don't expect you to just memorize the math. I expect that I can't do the math. I can derive it because the derivation is fairly straightforward if you know what you're doing, especially when you have ChatGPT to help you. But understanding how to get there is important. It's a question, did this whole process make sense? You guys here? Zoom, questions? No? Okay, so here's the thing. So here's the overall model. X goes in. The encoder computes the mean and the variance of Q for X. That's giving you the posterior distribution, approximation to the posterior distribution of Z. So then you're going to sample a Z from it, pass that through the decoder. The assumption is that the noise, E, is just added to the output of the decoder. Very often we also assume that the decoder itself generates estimates the variance of the noise. So the decoder will have two outputs, the phase and the variance of the noise that's moving it off the manifold. And so then the final output is going to be the actual phase. We are going to be maximizing the log likelihood or minimizing the negative log likelihood of the actual training data, which is essentially the same as minimizing the error between X after the noise and X before the noise. But because Z is being sampled from Q, the whole error actually ends up being a function of Z. And because this error therefore is a function of the decoder parameters. And because the Z is being drawn from a distribution computed from the encoder, the error also becomes a function of the encoder parameter. So it's very magical. You have, if I were to draw this whole thing, I have X going in here. I have the encoder. I have Q. And Z is drawn from this, right? And this goes through the decoder. This generates X hat. Then this X hat supposedly has some noise being added to it. And this is X. This is the overall process. And the magical thing we are doing is that we are minimizing the error only between these two guys. But in minimizing the error between those two guys, we are actually learning the encoder and the decoder parameters. Make sense? With an extra constraint on Z itself, right? That over here, Z comes from a standard Gaussian. Any questions? No. Okay. So where do neural networks come in? The encoder and decoder are both neural networks. The encoder has a neural network which computes the mean and the variance. The decoder converts the Z's to the phases. And so once you train the VAE, if you want to use it for generation, the VAE has now actually learned a manifold, and hopefully it's learned a very tight manifold such that the error is actually a statistically independent Gaussian noise of the manifold. And it's learned this manifold such that the Z's on this manifold have a standard Gaussian distribution. And so now if I sample a Z from a standard Gaussian distribution and put it through the decoder, it's going to generate a real phase. That makes sense to everybody? Everyone? Any questions? Okay. So the encoder is the statistic. So here's the overall model. The encoder is a statistical model that computes the parameters of a Gaussian. The decoder of the conditional probability distribution of Z given X. And the decoder is a statistical is a model that can take samples from Z. The decoder is not statistical, but any input from a standard Gaussian should be converted to something that's pretty close to a phase minus some noise, right? Okay, let's see how this works, right? So works quite well. And here the encoder is only needed for training. If I'm thinking of a generative model, the only thing that's needed by me is the decoder itself, because now I can take the decoder, I can feed the z's, random z's drawn from a standard Gaussian, and it's going to generate whatever data I've trained this for, like a phase, okay? And the z is, but then the encoder has its own purpose in that the encoder is actually training a Gaussian, but it's actually learning a Gaussian on the, it's learning a mean and a variance for the Gaussian, and the mean is basically saying on this manifold here is the most likely value of z that generated the data, right? Or the pre-image of this guy. And so, okay, here's your final point. Okay, someone on Zoom, can you tell me the answer to the first question? True or false?
It's true.
True. True.
Okay. Someone in this room, is the first statement of the second question true or false?
True.
What about the second one?
True. Also
Third.
true.
What about the third?
That's true.
All of them are true, right? The decoder, the whole business of the decoder is, you know z's come from a standard Gaussian. If you feed z's from a standard Gaussian to the decoder, it's going to generate things, yeah.
Don't we need the mean and variance?
So no. So the mean and variance are being estimated for a given output. So what was Q doing? So just to make sure that you don't lose the idea entirely, let's say I have this curved manifold and I've flattened it, right? If I flattened it, then it's going to look like the same dimensionality as Z. Please don't go up, okay. Now, anything from the standard Gaussian is going to generate a phase. If I see a specific phase, can every point over here have generated that phase? No, it's going to be some point here. So what Q is saying is for this phase, the Z's came from here. Does that clarify? Okay. So here are some examples from the original paper. They trained a VAE on MNIST data. Then they excite the decoder with a standard Gaussian out pop digits, right? Here are some examples of from a VAE trained on faces. And then you excite it with standard Gaussians out pop faces. And it turns out it's very easy to train. I want you to keep track of one thing. Do these look like clear, precise faces, or do they look like fuzzy faces? Fuzzy faces. So if each of them, if I have, if I pass a real face through the training data, the output is going to look a bit fuzzy, right? So is the error between the actual face and the real face going to be noise, or is it also going to have some characteristics of the face itself, like maybe the edges? What would happen here? So let's say this were from the training data, right? This is a fuzzy face, right? So the error between the actual face and this guy, is that going to have a face-ish outline, or is it just going to be white noise?
It will have a face-ish.
It will have face-ish thing because it's like this is a low-pass filtered face, right? And so what does this mean? It means that the error that we got is not truly statistically independent of the data, right? So the model is doing a pretty good job, but it's not doing a perfect job. Okay. So another thing, if I give it a face, so you can do some funky things with it. So I can give you two faces for a person. One of them is a happy face, the other is a sad face. I pass it through the encoder. There's going to be the Z for the happy face. There's going to be a Z for the sad face. I can connect these two, and if I look at Z's along this line and pass them through the decoder, you can see the transition from happy to sad. It actually learns the latent structure. It's actually very cute, right? So the VAE is a simple statistical extension of the encoder. It's an excellent generative model for distributions of data. You have various extensions like conditional VAEs, which model conditional distributions. The literature on the topic is vast, but of things that are related to what's going to come in the next lecture, which is going to be done by Asa on Monday. She's a fantastic teacher. This has to relate with what I just showed you. Two topics. First, given a Z, we could not find which region of the input could have generated that Z. That's because the decoder was a complicated, non-invertible function, right? But what if the decoder were invertible, so that if you give me a face, I can go back and say, this is the Z that produced it? Then what would we do? You'd expect the overall model to be better, right? Make sense? And so that is what is called a normalizing flow model. A normalizing flow model is a modification of the variational autoencoder, where Q doesn't have to be an approximation anymore. Q can be exact, because for every Z you can go back and find every X, you can go back and find out the Z's that could have generated it. Make sense? Right? The other thing is that we found that those faces were not precise, right? The edges were not great. So what happened, without even going into this, we had a standard Gaussian here, and that went through the decoder, and it was supposed to produce a sample from a phase distribution. But the fact that the faces are not precise meant that it did not quite manage to modify the standard Gaussian all the way to this complicated distribution for faces, right? Make sense? If the input had itself been something that was closer to the distribution of faces, you expect the decoder to have been able to do a better job of converting it to the distribution of faces. Yes or no?
Yep.
Okay, but where does this guy come from then? Where would that guy come from? Anyone? Perhaps you've just seen where it came from. Have you, Ibrahim?
Another variant.
The variational autoencoder gave you something that was closer to a phase than a Gaussian, right? How about if you pass that through a second variational autoencoder? It's going to be able to refine it even more, right? Make sense? You can keep nesting it. So you can actually start with a Gaussian and keep staging the conversion, morphing into the full proper distribution for faces. That makes sense? Right? And if you do that under specific conditions, where if you assume everything is Gaussian, you actually get a diffusion model. Make sense to everybody? It's all very pretty, right? So long as you get the basic idea. Questions? No? Thank you.